All right, so I am Luke Parham. This is a little intro to me. I'm an iOS engineer at Fusion. We're a company that does like 3D photography, is like the simple way to say it. And so I'm also a semi-pro Rocket League player, which is not true. I'm really bad at it compared to my friends, but I like it. So anyway, this is an example of a fuse. So it's an image that you can like touch and move around, right? So it's 3D. And so this is what I work on mostly, is the viewer for fuses. And so I've had to do a lot of performance-related stuff because we have, in our app, we'll have a feed full of these, right? And the users can interact with them while they're scrolling the feed. And if you don't do that correctly, then you can really get some laggy scroll performance. So I'm bringing some of the lessons from that here today. So first of all, we're going to go through why you should care about performance or any of the stuff we're going to talk about. And it starts with a story. Back when they were working on the Apple II, everything was going great, right? They were a new computer, making cool stuff. But the problem was that it had such little memory that whenever they booted, they needed to go to disk to get everything they needed to boot. And this became a really big bottleneck, and it ended up causing situations where it would take like many, many minutes to boot your Mac. And naturally, Steve was not happy about this. So he went and he told a little story to the team to get them motivated. And he said, let's say you can shave 10 seconds off the boot time. If you multiply that by 5 million users, that's 50 million seconds every single day. Over a year, that's probably dozens of lifetimes. So if you make it boot 10 seconds faster, you've saved a dozen lives. That's really worth it, don't you think? And this is kind of, not the best logic, because you guys could all delete Twitter right now and save like millions of lives. But it's still a fun story. I like it. So anyway, here's the game plan for today. We're going to go over performance and rendering. We're going to talk about kind of how things work on iOS just to get a good grasp of what we're dealing with when we look at these traces. Then we're going to jump into Time Profiler. And then we're going to end things off looking at the core animation instrument. So this, I don't know if this was obvious, but this talk does focus on like performance of your app, right? So these are kind of the two main ones. There's also System Trace. That's another good one for performance. But that one's a lot more rarely, very useful. But these are the two we'll look at mostly today. So starting off, performance and rendering. All right. So performance in iOS. There's a few things you need to consider when you're thinking about it. First of all, you need to think about the main thread. This is pretty commonly known in iOS, but the main thread is responsible for accepting user input, touch it, taps, swipes, stuff like that, tilting, and then displaying results to the screen. So basically, input comes in, and your app reacts to this input, and the screen changes. That's the simple way to describe an app. The goal should always be for your app to render these changes in 60 frames per second. Why is this the goal? Well, because it's basically, I'll get back to that. I messed up. Anyway, the goal is 60 frames per second. That means 16.67 milliseconds per frame. So that means that any work you do on the main thread, each chunk of work shouldn't take any longer than 16 milliseconds. And the kind of a bummer about this is that system overhead itself takes like 5 milliseconds. So at the end of the day, you only get like 10 milliseconds per frame. And if you go past this, then you drop a frame. The system gives up on drawing it. And then when you're thinking about performance, there's the idea of speed, which is just raw speed, right? How fast does your code go? Versus perceived speed or responsiveness, like how responsive, how good does your app feel? A lot of times you can do little tricks that even if you don't make your code any faster, you make your app feel better. And that can be more important at the end of the day. So dropped frames, blocking interactions. Say you hit a button and a view controller is supposed to be pushed. If that sits there for like 3 seconds, your users start getting a little like anxious, right? They start wondering like, did my tap work? Like, is this app frozen? What's going on? And the more you think about this kind of stuff, the more you become attuned to it. Like, the more you become a hater, you'll start using apps and just like hating on them because they suck. But and this is directly tied to user conversion and profit. Like Amazon, in the web era, like this is a thing. Amazon ties this to conversion of users and profit in their apps, stuff like that. Similar when you're working with mobile apps. So rule number one is that we're going to use CA display link to track dropped frames. So this idea of dropped frames, like when your main thread has too much work and it gives up on drawing a frame and causes stutters in a scroll, we're going to track this and see, when is this happening and where should we start looking for performance problems. So, demo number 1. All right. Okay, so here we are in Catstagram, and it's a pretty cool app. Kind of like this other one, I know. And I'll show what's going on up here. Hopefully you brought, if you had an older device, it would be useful because it's more obvious, when these problems are apparent. But it's not necessarily, oh crap. Not the biggest deal if you brought like a brand new device. You should still see some problems and still see some improvements. But either way, you can follow along. So first thing we're going to do, add a display link to our app delegate. So first things first, is everybody ready? Is anybody not ready yet? Anybody having trouble finding the? Okay, cool. I'll wait a second. But for everybody else, just head to the app delegate. And that's where we'll get started. Okay, so first things first. So what is a display link? A CA display link is basically just a timer. It's a fancy timer that instead of you deciding how often it fires whenever it's ready, whenever the system is ready to draw its next frame. So the nifty thing about a display link is that, say you have too much work going on the main thread. If you say you have 100 milliseconds of work, your CA display link that is firing here will not actually fire until the system is ready to draw the next frame. So to get started, we're going to have to do a little so in the callback that gets fired, we're going to do some calculations and figure out if a frame has been drawn based on the timestamp of the last time it was fired and this time. So first thing, come up to where it says private, it's line 36 for me, this root view controller. And we're going to add 2 new properties. So first is the first time. This is the first time that the, sorry, one sec, let me go 0. So this is the first time it's fired. We'll track where the app started, and that way we can see, at what point in our run a frame was dropped. And then for the second one, we'll do the last time. So this is just when was the last time we recorded, this event happening. And then we'll set these both to 0. Make sure that builds. All right, cool. So now that we have these 2, just scroll to the bottom and find this. There should be a comment here that says we're going to add a CA display link. So here we'll create the display link. So let link CA display link. And then when you make a new display link, you have to give it a target and a selector. So in this case, we'll just make the app delegate the target. So we can say self. And the selector, it doesn't exist yet, so let's leave it blank for a second. It'll complain, but. And then just to make it stop complaining, we'll make Objective-C. So this does have to be an Objective-C method. Update. All right. So we'll call it update. So every time this updates, we'll get our CA display link will be passed in right here. And so then for the selector, just make sure you call update. And now it should autocomplete for you. And then since this CA display link is just like a regular timer, you go ahead and add it to the main run loop. We'll probably talk about the main run loop a little bit more later. Basically, your app is a big while loop, right? Like I mentioned earlier, it waits for input and reacts to it. So we got this big while loop that's running, and we want to add this timer to that run loop so it actually gets fired. So let's see. just do link and then call add. And then here you can just say main, it's period main. And then for the mode, let's see. Yeah, you can just do that. So you can do .common modes. And common modes is just the default, basically. This means all the events that happen for a normal, default run loop. So once you have that set up, this will start getting fired every time the system draws to the screen, right? So this link, it has a timestamp variable, and that's what we'll use to see if a frame has been dropped yet or not. All right, so first of all, if these are 0, we can just go ahead and time equals 0. We want to check and see if they're 0. If they are, then we'll update them. The first time will be the current timestamp. And then the last time will also be the current timestamp. All right, so then once you got that set up out of the way, we'll just do some calculations. So we'll let current time equal link.timestamp. Grab that. So we want to get the total elapsed time. Basically, at any given point, we want to know how long the app's been running. This will be useful later when we start using Time Profiler. Oops, it's an equal sign. And then to get the elapsed time, in addition to how much time has happened in all, we want to get how much time has elapsed since the last frame was drawn. So to get elapsed time, we just say floor. We'll do current time minus last time. And then I'm just doing a little bit of extra math here, so we'll multiply it by 10,000. And then divide by 10. So this is kind of a way to just round it, make it a little prettier because it's a float, and make it to where it's actually printed out in milliseconds. The key, way we want to look at this is in milliseconds. The current timestamp comes back in seconds, I think. So yeah, we just want to do that to convert it. So then now we can think about that 16.67 milliseconds I mentioned earlier. So just to reiterate one last time, as your app's running, it renders 60 times per second, right? That means in every second, every time you render a frame, it has 16.67 milliseconds to do that rendering. If the elapsed time was longer than that, then you know frames have been dropped. That means the system didn't draw those frames, and you got a problem. So if the elapsed time is greater than 16.7, we're going to do some printing. Okay, man. All right. So basically, if we drop a frame, then we just want to alert ourselves to this fact, right? Just print that a frame was dropped, we had this many milliseconds elapsed, and we're at this point in our run of the app. And then finally, just make sure you update that last time to the current time. Oops. Yeah, timestamp. At the end of it. That way, this will actually update and be useful. All right, so now that we have this set up, we can go ahead and run our app. And hopefully I'll start scrolling around. We'll see how this does. So yeah, you can see that this feed is obviously a little sluggish, right? Kind of dropping frames whenever you scroll. Clearly not hitting that 60 FPS target we're going for. And if we come over here, we can see that we do have these. Oh, let's ignore that. frame. So if you, right here, there's where you can narrow this down to only prints involving frame. So as you can see, it's pretty much continually dropping frames. And we have various amounts. Let's go ahead and kill this. But right here we can see 133 milliseconds, 1,000 milliseconds. So yeah, you divide this by 16.67, and that's how many frames you've dropped in this chunk, right? So ideally, you want to see as few of these prints as you possibly can. That's pretty much the goal. If you're doing any work at all, you'll probably see a few of these frame drops, but anything crazy like this is not a good sign. So your goal should always be 60 FPS, right? It's like a aim small, miss small, like the Patriot. So anyway, now that we've got that set up, we can go ahead and move on to actually doing something about all these frame drops. We know there's a problem, but we don't know exactly what's causing this problem yet. So, all right, so like I said, use the CA display link. This is the code, in case you want to go back and look at it later. And now we can jump into talking about instruments. So naturally, there's a few places you can go to kind of get an idea of why frames are being dropped, right? The first place, a lot of times you may want to start, is just looking at the debug gauges. They don't tell you, they tell you a little bit of information, basically. They kind of clue you into the fact that there might be a problem. Especially the memory one, if you see big memory spikes, or the CPU one, if you see it, flatlining at 100%. Like, it'll clue you into things like that, but you can't really interact with it. So a lot of times you'll just look at this for a couple minutes, and then you'll be like, okay, well, let's move on to Time Profiler or one of the other instruments and see if we can't figure out why things are going wrong. So in case you've never used instruments before, this is what you'll see when you first run it. There's quite a few of these templates. One thing that is interesting to know is that there are many instruments, right, inside of instruments. And each of these is a template. So you can mix and match these instruments in any way you want. So like the core animation one, for instance, has the time profiler built in, and then also has extra core animation stuff on top of that. Same with a few of the other ones. So if you think you want to use energy log and time profiler, you can go ahead and make a new template and then save this in the custom ones up there on the left. So when you're using instruments, there's a certain workflow you'll kind of want to use. It's pretty similar to like the scientific method, right? You'll decide there's a problem. So we decided that. We used our display links to see that clearly our scrolling is bad. Then you want to analyze the instruments. You want to jump in, see if you can find what the problems are, think of some reasons to fix it. You want to form a hypothesis. When you see stuff in instruments, it can only point you in a certain direction, right? It can say, well, maybe you have a problem here. So you'll form a hypothesis, think of like one thing you want to change to improve this stuff, change that code accordingly, and then you verify. So change it, jump back into instruments, make sure what you did actually improved things. With our FPS thing we did, you can easily go back to that math and kind of keep track of the average, frames per second in that math we did earlier. So if you have an average FPS that's being printed out, you can kind of make sure that improves, right? And then if it didn't, you decide there's still a problem. And if it did, then you break the loop and you're done, right? But this is kind of you never want to just jump into instruments. I mean, unless you're learning, right? You can jump into instruments and do whatever you want. But usually you want to have a goal, something you're trying to fix. So here's what, once you start looking at Time Profiler or one of the instruments, this is what it'll look like. Up here is the toolbar. These are all the buttons and controls. First, there's the record button. That'll start you in a session, and then you can hit the stop button once you're done doing what you want to do. Then there's this chooser where you can choose what device you're profiling on and also what app you're looking at. Usually you can only work on one of your own system apps or one of your own apps. But if you have a bunch of phones hooked up, you can swap between phones up here. Here you can see which run you're on. If you run this more than once, say you're doing a few profiling and you make changes and you keep reprofiling, you can keep all these runs up here and kind of toggle through them and see what's changed from one to the next. Then over here you have a few controls to kind of change what's in the panel. So here with the plus, you can add a new instrument. If you want to make a new template, you can always add more instruments to the existing template. Strategies, this allows you to change between looking at things in terms of threads versus looking at things in terms of cores. There's like a few different ways to look at the data. And then these are just a few buttons like in Xcode. You can close and open the panels on the right and bottom. So then we have the timeline. This is where, depending on the instrument, you'll see kind of graphs here usually, like how are we doing over time. This is showing, if you look in the middle, that's the CPU activity at that chunk in time. And you can always, you can click and drag and zoom in on stuff, so that's nice. And then down in the detail pane, depending on your selection up top, it'll show you the results of what's happening at that time. This also depends on the instrument. For Time Profiler, it's method names. For the memory instruments, it could be method names. It kind of depends on what you change over here. So for challenge number 1, this is just to get you guys familiar, get you in there, and kind of, break the ice. So basically, you'll want to run instruments and get comfortable. Just start the app in profiling mode, try a few of the instruments out, just kind of play around. And yeah, start a Time Profiler session, and then see if you can zoom in on one dropped frame. You can see the dropped frames in the console, so I'll show you guys that in a second. And that's your goal for now. Before you do this, I'll jump in and kind of click around real quick just to show you things before you mess around too much. OK, so to start instruments, there's a few ways you can do it. The easiest way, the one I prefer, is Command-I. Just hit Command-I. That'll start instruments running. One important thing, this should be the case for this app, but if you're working at home, you want to go into your build settings and make sure you search for dsym. So this debug information format, make sure this says dwarf with dsym. If it's just dwarf, you won't be able to see what any of the method names actually are. You'll just see hex values. So if you ever are using Time Profiler and it's just a bunch of hex values and you don't know what that means, you can come in here and make sure your dsyms are turned on. So the other option, you can click and hold this play button, and it'll actually give you all these options. So you can run, test, profile, or analyze. This is kind of nifty because it changes this to a wrench, which I also like. But either way, Command-I or wrench, up to you. And then this will build in release mode. So as you can see, it's taking longer to build this time. That's because it's kind of building from scratch. And then as long as that all worked out, we should have this instrument chooser, pick the template. Today, like I said, we're going to look at Time Profiler and Core Animation, but feel free to look at any of these. I mean, they're all useful at their own times. But I would say Time Profiler, Core Animation, and then like leaks and allocations are the other two that are nice for memory. But anyway, so yeah, once you choose one, it'll start this up. Over here, we have the record button. If you want to hit that, it'll start the session. So now it's collecting data. Usually, you just want to play with your app for this part. Just kind of scroll around, make frames drop, do stuff your users would usually do. And then, as you can see, this is always changing. We have all the methods that are being called collected here, and this is dynamically updating based on how frequently they're called. And then we have our Time Profiler timeline with CPU percentages as you go. So once you feel satisfied that you've captured all the info you need, you can come over here, hit stop. And then the final tip before I let you guys just play around is you can click and drag, and this will update what's down here. So you can also, depending on if you have a trackpad, you can like pinch to zoom on this. If you don't have a trackpad, you can option scroll, I think, and that'll also zoom in. And then so you can play around with which pieces of work you're looking at. So this is kind of what you should have seen. If you have this thing over here, you can click on it, and you can switch from the detail view here to the console. And this will show you the same console that you would see in Xcode. And then there you can see, here's all the dropped frame messages. And up in the top, in the timeline, you can zoom in. So say you can pick, like, oh, I see some dropped frames here. It happened around 11 seconds into my run. So I can go up here and find the 11-second mark, see the chunk of work that was happening, and kind of say, OK, well, I know a bunch of frames were dropped here. It's probably this chunk of work that was making that happen. Then you can, click and drag to focus on that and see what was happening there. So all right, it's Time Profiler. Let's get more into this. All right, so at the bottom we have the call tree. Let's go ahead and explain what exactly this call tree is, because it's not super obvious. So basically, when you're running your app, Time Profiler is sitting here collecting data, right? What is the data it's collecting? Well, basically, let's say you have an app that is set up like this. This is a super simple version of an app that starts with main, and then it calls a few methods. So it calls foo calls bar, blah, blah, blah. So this is kind of showing the flow of an app that calls foo, then it calls bar, then it calls foo. And then there's sub-methods that get called as a result of that. At any given time, you have a call stack, right? You have functions that are being called, and they're being added and subtracted from the stack. So basically, Time Profiler will take a snapshot at a given time. I think it happens every millisecond by default. So Time Profiler inserts itself into your app. It takes a snapshot of your stack trace. So at the beginning, this stack trace is main, foo, bar. These are the functions that have been called so far. So it grabs that stack trace, and it saves it off. And it's like, OK, cool. This is what has happened so far. Millisecond later, it takes another snapshot. And so this time, it's main, foo, and bar. Same thing, right? So it brings it over, and now it bumps each of these counts up. So you see main's been called twice, foo's been called twice, and bar's been called twice. Then on the third one, we have main calling bar. So this is a different stack than we saw before. So instead of just upping all the numbers, we make a branch in our tree. So instead of just a call stack, now we're starting to have a tree where main calls foo, and then sometimes foo calls bar. Other times, main calls bar directly. So these are the two possible options for what's been happening in your app. Then on the last one we'll look at, we have main calling foo, calling baz. So once again, this is a different split. So we pull that over. And now sometimes foo calls bar, sometimes foo calls this baz method. And then the interesting thing to notice here is this baz got called, right? And over here in our call tree, it says 1. It says this has been called 1 time. But if you look up there, it's been called 3 times in reality. And this is just something to know about how it works. When Time Profiler is showing you these numbers, it's not actually how many times this method has been called, and you're not actually tracking how long these methods have been running, like strictly this method runs for so many milliseconds. Basically, you're getting an average. And the thing about that is, if a method is small enough that it's not getting captured by these stack traces, then it's small enough not to matter. And even if it's super small, and if it's being called millions of times, odds are it's going to show up in one of these traces. So it kind of all balances out based on these averages. So baz is small enough that it only counts for 1. All right. So when you're looking at this, this detail pane, I'll show a quick example. This is pretty important, but yeah, I'll come back to this. All right, we're in a trace right now, right? And so here we have catstagram. This is separated by thread right now. So we want to look at the main thread, right? This is where we said if we have frames being dropped, that's where it'll happen. So you can click on this little arrow, drop, and then we have the main function. So like we saw just now, that calls UI application main, that calls application run. So you get a lot of kind of not so interesting stuff here. It's a little interesting. But one cool tip is let's say we close this. If you hold option, and then click one of these disclosure arrows, it'll automatically open all of this. And it basically just kind of magically opens to what is the most significant stuff in this subtree. So if we come down here, we see this CF run loop run, and then all these other CF run loop things. So that was kind of the point of this here slide. That is kind of where you live. When you are in a trace, basically always, if you do this option click and drill down, you'll get to the CF run loop run. And that's because, like I mentioned earlier, the run loop is just this big game loop, and it's collecting these events and making things happen as a result of that. So just knowing that this is kind of how your system works helps not be overwhelmed when you come in here and see all this bullcrap that you may not care about. So then kind of an interesting thing that seems to happen is that if you option click on these, you'll drill down and you can see some stuff happening. A lot of times these will end up containing your big bottlenecks if you drill down into these CF run loop things. So you can click through observers, see a bunch of core animation stuff. So that's just a quick preview. Let's go back to the slides. This is what you'll see all the time. And then when you drill down into that, you'll get one of your bottlenecks. So the main run loop, let's look at this a little more just to kind of get more familiar with it. The run loop, like I said, is responsible for event-driven model of an iOS app. It's like a game, basically. Things happen, and you respond to it. So your app starts, and it has all these methods that get called. But then once your app is running, this is basically all that happens. You have an event loop, and it just sits idly, sits and waits for events, and then does that until you exit the app. So these events, they have observers and sources. Basically, there's things that feed information into the loop, and then observers that watch for events to happen in the loop. And this is where all the work, when work happens on the main thread, this event loop is what dumps that work onto the main thread, right? So they're kind of tied together. There's a main thread and a main run loop, and the run loop is what's dumping all this work onto the main thread. This backstory is just, it's useful if you're going to dig through these traces. So each turn of the loop, is responsible for responding to events. And, it submits work to the main thread. So challenge number 2, now that we've had an intro to things, is to jump back into Time Profiler. And basically, I want you guys to dig through the call trees and see if you can't figure out what you think the top 2 or 3 bottlenecks are. This app obviously has a lot of problems, so basically, we're going to spend the next 15 minutes digging through. I can come and walk around and, just basically pretend you have a piece of paper. If you have paper, just write down, I think this method is causing the problems. I think doing things this way is causing problems. See if you can't kind of come up with your own ideas for why this app is slow. Hey, okay, cool. So one quick note that I just said over here is, you may notice when you zoom in on something, like when you narrow things down, all of your console output just disappears. And it's expected, and it seems like, I don't know if it's a bug or just bad design, but you would think it would show you the console logs that happened during that time, but it just doesn't. It just kills everything. So the zooming in part is only useful for narrowing down which methods you see in the call tree. It just breaks your console. So just something to keep in mind. So just in case you're in the middle of looking, one kind of useful thing is if you come down here to the call tree, this button gives you a few options for kind of changing what you see down here in your methods in the call tree, right? So by default, you have separate by thread. This is the thing that makes it so that we see the main thread here, right? If you turn that off, you'll just see all the work jumbled together. But I usually keep this on because it's just nice to see, okay, this is main thread, and these are all your background, like, worker threads. Then you have invert call tree. What this will do is it'll take everything that's at the leaf, right? As you drill down, these are the leaves at the end. This will take your leaves and float them to the top and kind of flip everything upside down. So it can be pretty useful, like, as someone saw earlier, like, it can just kind of put all your bottlenecks to the top if you can read it, basically. I think it's pretty good to use. I kind of toggle back and forth on it because sometimes I just think it's annoying to read everything backwards, and I just like to drill down. But that's just me. Hide system libraries, this one's a little more significant. So this one will hide all of Apple's code. So system libraries are things that Apple writes and you can't control. So a lot of times it can be kind of tedious and annoying to look through all Apple's code if you didn't write any of it and you don't really know what it's doing. So this is a pretty nifty one where if you have some really bad bottleneck in your code specifically, turning this on can make it a lot easier to find it. And then flatten recursions. Say you have a method that recurses on itself and it fills up your stack traces. You can just flatten recursion and it'll show it one time instead of a bunch of times. And then top functions, I always forget what it does. But Oh, it changes the percentages over on the side. So, and that's one more thing we should talk about real quick, is over here we have our weights, right? So let's undo this. So if you look at the weights, there's a regular weight and self-weight. And here you see a lot of the self-weight is 0. But basically the weight is how much of the work in this particular thread or whatever is in this subtree. So if you see, what's the second one? 52%. So we know that 52% of the work that's happening in the app is happening in the subtree of the main thread. If you look at the self-weight, it's 0 seconds, right? So that means literally in this method, not counting any of the methods it calls, how much work is happening. So in the main thread method that gets called, nothing is happening. It's only calling it into its, other methods to do work. So a lot of times this self-weight, I find that self-weight a lot of times ends up being a lot of times you'll see it be 15 milliseconds or 30 milliseconds. And then okay, this method is, a big chunk of the work. But a lot of times they'll all be 1 millisecond. You'll drill down through a whole tree and it's 50 things that are 1 millisecond long. So, it's kind of hit or miss on how useful that is. But it's good to know what the difference is between weight and self-weight. And then these icons here, they just indicate what library this method comes from. So you can sit and hover on it and see that the person means, oh, that's the user app. So that's Catstagram itself. UI kit, core foundation. So yeah, you can just kind of hover on these. I don't think the icons are super intuitive, but at least it tells you what they actually are. So, and then over here, you have the heaviest stack trace. So basically, depending on any given subtree that you've clicked on, this will show you what the heaviest, the heaviest stack trace is. This will show you where the most work happens in that particular subtree. So this can actually also be super useful for kind of just, the first thing you see, oh, this is, where the most work is happening. And these darkened lines are where your code is that's not Apple code. And then that will automatically put you on them over here in the call tree. So I'll let you guys mess with things for another 3 or 4 minutes, I guess. Play around with that. Actually, I should probably extend it since I talked. Let's give it 7 minutes. OK. So we good? Move on. And then one last thing that I will, look at. You may or may not have noticed this, but basically, let's go ahead and hide system libraries. So when you come to code that is your own code, if you want to kind of zoom in, we have this crunch some numbers here, right? If you want to look at the code and see, okay, what in this method is actually doing all the work, you can double click on it here. And then this takes you down to this nice view. And here we see, okay, this line takes 1.7% of the work, and this one is 98% of the work. Very important stuff going on in here. And you can change this. I come up here to this little cogwheel and say view as value. So now we see 12 times and 684 times right here. So this is what I was talking about. We have stack traces, right? So that means this line showed up in the stack traces 684 times, literally, that got captured. I like the percentage better, kind of, but it's up to you. They're kind of the same thing. But anyway, you can click up here on root to go back to the stack trace. But anyway, yeah. So let's see. Anybody find any bottlenecks? Anybody want to raise their hand and be called on to tell me the bottlenecks? Yeah. What's up? What was it? Image decoding. Yep, that's one of them. Anybody else got anything? The report logs. Yep, that is one of them. So we have images, logs, crunch some numbers. Yeah, that happens inside the logs, right? Yeah, yeah. And how did you guys fix that mostly? Was it background threads? Yeah. I should have made that trickier. But yeah, basically, if we go back to our, circle of events, we've found some bottlenecks, you guys pointed out, and now the goal is to just pick one at a time. Usually, the higher up on this list it is, the bigger of a bottleneck it is. And then you basically just go through and try to think of ways to speed those things up one at a time. And that's the gist. And you go back in, do some more profiling. A lot of times, in my experience, there'll be like one or two big things that are the obvious causes. But that's not always the case. Like we saw, there was 5 or 6 different things that are happening in this app. So it kind of depends on your app and what is happening in there. But you said, why run it in release and not debug? So the point of doing that is basically you want to simulate the environment your users are going to be in, right? When you release an app to the App Store, it'll always be in release mode. So I don't know how big the differences are that you would see in a stack trace. You can run it in debug mode if you want, but there's no reason to really. Like, it's strictly better to just do what your users are going to do. So now I'm just going to run through and we can fix these bottlenecks together. There is definitely a hierarchy of which ones are causing the most problems. And let's see. All right, cool. So, like you guys probably did, let this load, do some scrolling, do some tilting. We have this sweet cat tilting animation. We got frames dropping like crazy. That's it. Cool. All right, so we've collected some data. We can go ahead and kill that. All right. So, just to recap on things, we have main thread here. If we zoom in on this, we can kind of get a better idea for what's happening when. You can come up here and see, 80% here. You can click on main thread, focus on that. So, let's just go ahead and option click. We'll drill down in here. And like I said, here's your run loop. So we'll just click through these one at a time and see what we had in this run. And based on the device and stuff, it can always be different. But for this, I'm running an iPhone 5 right now, so it's pretty particularly slow. And as people pointed out, this one seems, if we drill down, we have this NS fire timer, and then we run into our crunch some numbers. So let's go ahead and make things easier. We'll go ahead and hide system libraries. And you can option click to close, and then re-option click to open. And that'll clean, if your thing's all jacked up, that'll make it real clean. So this kind of nicely just lays out, okay, top thing, report logs. Second for this is we have this device motion callback. So we can drill into that a little bit. And then we have self-wrote index path. Oh, sorry about that. So let's go ahead and try and fix the logs real quick. If we drill down a little more, looks like this crunch for numbers is the biggest deal, like we said earlier. So we'll just go to app delegate. And actually, let's search for the logger. So we have log. We have this cat logger. If we go to that file, we do, like we saw earlier, if we come down here, we'll see that this number cruncher is a big deal. And you'll have to see right here, I call this. I should have got this return value and used it to make it more obvious that this has to run in place. So one good strategy for making your app more responsive is what a lot of people did here. They threw this on a background thread. And if you have some calculation that can run in the background, doesn't really matter, like nothing else depends on it, then that is a great idea. In this case, let's just pretend that we need this information for this logging to happen. So we'll keep this in place, but along the same lines, we'll fix it a little bit different way, but it's basically the same thing. And this is kind of, if you go back and look at this, we have this logger, and it's not really doing it's not just printing things to the console, right? It's doing a bunch of, making these headers, doing all this post data. So it's sending a bunch of info off to the server. And this is kind of a best practice for doing this server-based logging. Anytime you have a timer set up that just sends stuff off to the server all the time, That's kind of a red flag. If you used the energy instrument, it would red flag this and say, hey, like you have way too much overhead here. Fix it. So a kind of good rule of thumb for doing this kind of stuff is if you can coalesce these events into one, you should. And a lot of times this is kind of straightforward. If you're doing logging type stuff, you can just keep, saving these off into an object and then send it once at the end of the app run instead of throughout the app run. So to fix it, we'll go to the app delegate where this is being called. And if you come up here, right now we just make a logger and then we start logging, right? This starts this bad timer. Let's go ahead and grab that, delete it, and down here we have this application rule design active. This is a good place to do cleanup or like last-ditch things when your app is about to leave the foreground. So here we can go ahead and throw the logging, and this way it'll only happen once at the end of the run. It just won't happen during all your scrolling and stuff. So a little bit nicer. And instead of calling start logging, this is the version. Let's just pretend for a moment that you wrote a coalescing version that doesn't, require this to keep running over and over again. And we'll call this send logs. Actually, we'll call it something else. Report logs. So we'll just call this directly. Logger.report logs. So now all of your coalescing and stuff, that can happen inside the logger. You don't have to worry about that. But we'll just do this once at the end. And now if we run this again, so what we were doing in this particular run is we have this first line here, right? We have report logs. And we know this is our biggest bottleneck right now as far as bottlenecks go in this view. So we made some changes. And we'll see if they helped. So show this. So play around again. Looks like we still do have some frame drops, but it's not nearly as bad as it was before, right? It's a little stuttery here and there, but it's not consistently, slowing to a crawl. It's still pretty bad, though. So let's go ahead and stop it. Come in here and look at time profiler. Oh no, the curse. Okay. So this is a great example of how instruments is super unreliable sometimes. And in this case, we have all of my methods have turned to hex values. How do I fix this? I'm not sure. It's like the classic IT problem, like turn it off and turn it on again, and maybe it'll start working for you. So we'll kill this. Oh, dang. Okay. Once again, another bug with Xcode. So if you're on Xcode 3 or 9.3, then you probably saw this bug where you don't get any time profiler useful information at all. That's super cool. So let's see. Okay, cool. Okay, so apparently if you're running into this, you can allegedly delete derived data and it'll fix it. So let's try that. Hey, there we go. Cool. Okay, so finally. Do some scrolling, collect some datas. Go ahead and kill that. All right, so like we did before, we will hide the system libraries. We can invert call tree, just for fun. I don't think it makes that big a difference. And this time we have a different set, which is good because we went in before and we fixed our logging by doing it one time at the end, coalescing like pros. And then now we have this pan image, right? So it looks like this is our next biggest bottleneck. And we saw that we still have tons of frame drops, so we can go ahead and just dig into this. So it looks like we have this pan image that gets called inside of a callback. And let's see, like before we can... Oh, this is another... I'm showing you all the bugs. There's a lot of bugs in Time Profiler and the instruments. I don't know why. There's also no documentation, so you gotta fight through it. But sometimes you'll try to click into the code, and it'll just not show you any code. It'll just show you this, all of the code. So when that happens, that's too bad. But let's see. Undo that. There you go. So this time worked. So yeah, it looks like we have this print. So this is nifty. We have 35% of work is happening on this print. And then another 62% is happening on this panning. So the print is a pretty obviously unnecessary chunk of work. That does bring us to our next rule. And that is never do I/O on the main thread. So this is just something to keep in mind as a general rule. If you're ever going to disk and pulling stuff off, the hard drive, especially if you're doing, this seems obvious, but if you're doing networking, definitely don't do it synchronously and leave it on main. That'll kill your app. It's like hard to do that. But yeah, any kind of I/O really, you shouldn't, like if you're loading images, throw that on a background thread. So yeah, that's good to keep in mind. And then let's go back to our actual trace. So how do we fix these two things? Oops. Luckily, the print is an easy fix, right? And not only should you not be doing, so print is technically I/O. That's why I brought that rule up. You are printing to the log. More importantly, you shouldn't leave prints in production code. If you have an app and you have a bunch of prints in it, like especially if it's I think it's iOS 10 or earlier, they can add up to be pretty big bottlenecks if there's enough of them. So let's see. Oh, look at that. We're right. Oh, no, sorry. So if we can search for that print. We see that it's happening in the view controller, and that actually brings us to our motion manager. So here we have a motion manager, and every time this gets called, we're printing all this information. So easy fix. You delete that. Done. Easy. And then as far as the rest of it goes, we still have 62% was in just the panning itself, right? So if we drill in there and check that out, you can see that there's a lot of math going on, but it's nothing too crazy. Like if you drill into that method itself, the pan image method, the ending, right, the completion nil, just the bottom of the function is 97%. Everything else is like 0.7, 0.4. So like your math is not actually the bottleneck. It's just this whole method being called so many times. That's the actual bottleneck you're seeing. So if we come back out, basically this is one of those times where there's not like an obvious answer. Like how do I make this, be called less? But there are a few little strategies. One is the motion manager. You can actually tell it how often it should update. So its default is a little bit too much. So let's go ahead and change that. We can say motion manager. And let's set it to 0.2 motion date interval. So this way it'll only get called this is 200 milliseconds, every 0.2 of a second. That's plenty of time to have your cats tilt back and forth based on your motion. So that'll cut out a lot of how often this is called in general. And then another thing, so let's go ahead and run this real quick, see if that helped. I'll leave this here for a second. This is the main line you want. Oh, shoot. All right, so collect some. Zoom on the actual scrolling. I tend to do this, like, I kind of ignore the startup stuff if I'm looking at the feed scrolling, so I'll zoom into the chunks where I'm actually scrolling around, but kind of up to you. So if we drill back down, oh my dear God. You kidding me? I wonder, I have a theory. It happened when I didn't have my screen was locked and it failed. I wonder if that's why. All right, so did some running, kill it again, zoom in. All right, and now we can see that the top bottleneck has changed. It is now the table view self-road index path. So that means we've reduced the number of times that method was called enough that it's no longer at the top. It is the second thing still, so you can always do more. Oh, no, it's not. I'm sorry. I misspoke. Fetching the feed. Yeah, totally different. Height for road index path. Yeah, so this has moved way down here to the fourth thing in the list. Its weight is 0.7% of the overall work on the main thread. And it counts for 15 milliseconds. So this is nice. It literally accounts for 15 milliseconds out of the 2 seconds that we are looking at. So not a significant thing anymore. So as one person pointed out, and this is very key, we've actually kind of been fooling ourselves all along in this session. Because right now, if you look at this, you'd say, okay, like we have self-road index path. You can dig into that if you want, but there's not a whole lot going on in there. I can prove it, I guess. Update cell. Yeah, so we make an attributed string. We do some reloading. Basically, it's a lot of like setup and like little layout things, which one thing to take away is there's always room for improvement, right? Like if you see something that is a bottleneck and you don't think it should be, you can always, cache stuff, avoid calculations, avoid doing things unnecessarily. But in this case, this update is not a huge deal. But this whole time we've had this hide system libraries on. This can be useful, like I said, but it can also be kind of misleading, and it can end up being kind of a bad habit. So let's go ahead and turn this off. Do things the natural way. And now we see, so out of our 6.5 second run, 1.8, aka 27%, is on the main thread. If we drill down, we're back where we were earlier. We have our run loop stuff. And let's go ahead and look at these one at a time. All right, so it looks like we have, let's pull this up. What our new top bottleneck in this view is, see, if we close this real quick, it's totally different. It's a bunch of system stuff that we don't remember looking at before. So actually, no, wait. See, this one is self-road index path. So like I said, it kind of depends on the run, and it depends on what you're doing with your app, what you'll see in here. So this one is self-road index path. So it's basically the same. But let's run this again, see if we can collect some more data. Oh God, no. All right. If it shows me hex values, I'm going to lose it. Yeah. Okay, cool. Didn't do it. All right, so doing some scrolling. Got some good frame drops in there. Go ahead and kill that. Okay, so let's look again. All right, cool. So in this case, if we hide system libraries, we'll see what we saw a second ago. We look at main. Main has 40% of the work on it. And we see self-road index path. We see, now we're seeing the closure. And this closure is for fetching the data. We see did finish launching, app delegate init. So a lot of little stuff that is not very computationally intensive. And all of it says like 5%, 0.8%. So, but if we turn off the hide system libraries option, and then option click to close, option click to open, we still see main at 41, so that makes sense. But then if we come down to all our run loop stuff, let's look at our first run loop, do source 1. And if we drill down, we have this display link, commit transaction. Oh, no, this is okay, well, what can you do? It's actually surprising. Here, let's look at, so maybe if we want to hunt a little bit, we can go in our console and see these are our frame drops. Let me look at my code real quick. Okay, cool. So let's just try and look at some of these bigger ones. We have 116 milliseconds at 22 seconds in. So let's see if we can get anything useful out of that. Zoom in. $23. Okay, so right here we have 120%. Looks like a lot of work going on here. So let's zoom in on that. Let's see what the biggest thing is there. All right, so this is one of those times where looking at the console and seeing where the frames are actually being dropped is actually super helpful. I was kind of just relying on things working out. But so if we come in here and we look at where it was like 130 milliseconds of frame dropping. It was in this region where we have 130% CPU activity. And then if you do what we were doing before, where you hide system libraries, you will see table view self-road index path, update the link, and layout subviews. Like I was saying, those aren't a ton of work, but if you hide the system libraries, you'll actually see a totally different stack trace than you had seen before. And it's if you come over here and look at your heaviest stack trace, you'll see that it's all completely grayed out minus these mains up at the top, right? So that means every single method in this stack trace is code that Apple wrote. It's nothing that you wrote. It's nothing that you can directly influence. But it is 40% of the work in this range where you're dropping a bunch of frames. So you can be pretty confident this is exactly what's causing all those frames to get dropped. You won't see this at all if you have system libraries turned off. So this is kind of one of those places where, depending on how familiar you are with how Apple's stuff works, you might come in here, see this, and just kind of move on, right? Like it's very easy to see this and be like, I don't know what this means. I didn't do this. It's not my fault. So, but it can be useful to kind of read through here and get really familiar with it and Google things, right? If you see stuff and you're like, well, what does this mean? Like, what is this render create image? I don't know. And also, if you've watched a lot of dev videos, you might be familiar with what's going on here. So we can actually, if we look at a little closer, we can see that this is happening as a result of a CA transaction being committed. So if you were familiar with how UIKit and core animation works, basically, anytime you change your views, if you set up a view and you expect it to be displayed on the screen, what actually happens is at the end of the current run loop run, there is an implicit CA transaction that's created. We'll go over this a little bit more in the slides in a second. But basically, let's see. Yeah. Basically, there's a CA transaction that happens. This kicks something off to the render server so that your actual rendering can happen. So all of this stuff is kind of indirect stuff that happens. And if we scroll down a little bit, we see that there's this Apple JPEG decode all. So this is a private framework. It does all the decoding. And basically, if you've sat and thought about this long enough, you'll come to realize that this is JPEGs being decoded on the main thread of your app. This is a necessary thing. If you have image views that are showing images, odds are they will be JPEGs and they will be decoded. And depending on how many images you have and how big the images are and how intensive it is in your app, this may or may not be a concern to you. Like you may see it, but you may not have frames dropping, so it may not matter. But in our case, it's pretty much the only thing happening at this frame drop spot. So we know that this is our bottleneck, and we want to try and find a way to work around this. And luckily, there is a way. So that'll be our next demo. Rule number 3 is always decode your JPEGs in the background if it's necessary. If you use any kind of image framework, this will happen for you pretty much automatically. If you use texture or pin remote image or any of the other ones, they pretty much all do this. So, but it's cool to know how to do it yourself. So let's go ahead and, in this case, what we're going to do, so what you can do is instead of letting Apple do the JPEG decoding for you, you can actually manually decode them yourself. There are pros and cons to this. This decoding, you'll use a CG context and do some drawing. This is technically this is one version of what's known as off-screen rendering. So what that means in this context is you're writing this code, and it runs on the CPU. And this CPU code is just designed to render an image into a bitmap. You'll notice that it takes in a UI image and spits out another UI image. So any given UI image can be backed by a already decoded or not yet decoded image source. Unfortunately, there's no way to actually tell one way or the other which one it is. So you kind of have to keep track of this on your own. You'll have to cache these. The decoded ones, they are decompressed and pretty big. So depending on your images, they can take up a lot of memory. So you want to be careful with this. But if you know what you're doing and you plan accordingly, then it's a good way to get some work off of your main thread. So if you zoom in here, you can see we set up a context, we do the drawing, and then we return this decoded image. So this is technically less efficient than letting the image view do things itself. If you compare them one-to-one, this usually ends up being slower. The UI image view is GPU accelerated, and it's got a lot of special things under the hood that you can't get access to. But when you do this, you can throw this onto you can use a global queue, you can make your own queue, but you can do it concurrently. So this is a concurrent global queue. You can throw these image decode operations on there, and then if you have a 4-core device or whatever, you can be decoding 4 of these at a time, and all of this will be happening off of main. So it should end up kind of being faster, and it won't block main at all, which is pretty nice. So demo number 3, we'll decode some JPEGs in the background. All right, and so for this, to accomplish this, we're basically going to make our own UI image view class and replace the UI image views that we have in our cell right now. So first things first, let's see. Come over to the view folder and make sure you're inside there and hit Command-N. We'll make a new Cocoa Touch class. We'll name it async image view. It's a UI view subclass, and it will be Swift. It goes in the view folder. Cool. You can just delete this comment. All right. So basically, all we're going to do is we're going to make this a view that will take an image property, and when it gets an image, it'll do the decoding asynchronously off the main thread, and then whenever it's done, it'll show the image. So you will have this delay, right, where you've set the image and it won't quite show yet, but you'll just have a placeholder. It'll be a gray background. So it's not really a big deal compared to dropping a bunch of frames. So for this, you can do this multiple ways. You could do like setters and getters. I like to use private variables because I like Objective-C and stuff. So you can do it however you want. But we have this image, UI image. So we'll use this for the actual backing, and then we'll use computed properties. So we have, var image. So here we'll have a getter and setter for when they pass in this image. Get, set. So yeah, just set up this backing image variable, and then we'll write these two for the getter and the setter. When you get, all you need to do is return that backing image. And then when you set, this is where we'll do the decoding asynchronously. So first, we'll say the backing image equals the new value. Then what you want to do is you want to set the contents to nil. So equals nil. If this is something that's useful to know before you start doing this. A UI view is backed by a CA layer, right? A CA layer has a property called contents. This can be a CG image, a few different things, but basically the contents are what defines what will be shown on screen. So once you get a new image, you want to set this layer's contents to nil to get rid of that old image if you're reusing this. Next, we want to guard against a nil image. Or we want to guard against if you're reusing the same image. So let's see. New value. Else. Return. And then once we've got that done, we can go ahead and... Oh, sorry. Anyway, this guard will make sure that it's not nil. If it's not, then we'll actually want to do the decoding process. So next we will jump onto a dispatch queue. We can grab a global one. In this case, we'll just do the user initiated. And we'll throw this async job on there. And basically, we're just going to get a decoded image while we're in the background. And we're about to write a category on UI image that'll do this. So let's just pretend we have the code we want. We say decoded image for the image that got passed in. This doesn't exist yet, so you can comment that out, or you can write it afterwards. But yeah, we're going to get a decoded image. And then when we're done with that, we want to jump back onto main. Anytime you're updating a view's properties like its contents or its bounds or anything view related that you want to update, you want to make sure you are on main for that. So basically, if you can prepare all your content in the background and then jump to main to set it, that's ideal. So now that we're on main, this is where we'll use our decoded image once we're ready. And now we'll just head over. We have this UI image plus extensions. If you do Command-Shift-O, you can search. So do UI image plus. You can find this extension file. This is where we're doing like our downloading and stuff right now. And right now we're doing this JPEG drawing, okay? So we'll call this decoded image. So it's a class function or method, but it's a func. And decoded image. So it takes in a regular image, returns an optional, because technically this decoding can fail. First, we'll guard, let's see. And we'll make sure that, okay, cool. We'll make sure that the image passed in has a valid CG image. So guard. So first things first, make sure that we can get a new image, and it's from this CG image. Otherwise, we'll just return nil, because there's nothing that we can decode. And next, we're going to set up our context. So to draw an image, you have to use a CG context. So first thing you need is a color space. CG color space. And we'll use the RGB color space. Next, we'll set up our context. And this is a bit of a, let's see, CG context. Oh, classic. If it doesn't autocomplete for you, then that is a bummer. So mine's not. Whatever, I don't need it. So first you send in data. In this case, we'll just send in nil. When you're making these contexts, it's kind of one of those things where you kind of do the same thing usually. Like they'll all be roughly the same. So next we want width. We want to use the image's width. Height is the image's height. Let's see. The next one is called bits per component. Per component. So how many bits do you want to use? In this case, it's 8. It seems to always be 8. Next, we have bytes per row. And this one always seems to be the image's width times 4. Bit of a magic number, I know. Not finally, but next, we want to pass in the space. So here we'll pass in that color space we just made. And then finally, we pass in the bitmap info. So this is just some configuration for what kind of bitmap you want to create. Bitmap info. In our case, we want to do a, let's see, alpha info. None skip first. Yep. .RWD. So this is pretty wonky, especially for Swift. But in this case, we want to use we're passing in the alpha information for this bitmap. In this case, we don't care about alpha. So we're saying none, skip first. And that's basically it. We have color space and context. Now that we have those two set up, we want to do the actual drawing. So we can just say context. It is an optional, so it may have failed. And then we want to say draw image. And we want to draw it in a CG rect. So we got to find the draw image in CG rect. So find that one. We're drawing the new image. This is the CG image that we grabbed. And then we'll make a rect x, y, width, height. So just basically create the bounds for it. And you just want to make this the image's width and height. Cool. Okay. So once you've done the drawing, this will basically put the bitmap onto the context stack. So this drawing is done. Now you want to grab the drawing and put it into a UI image. So let drawn image equal context dot make image. This will return a CG image for you. And then finally, you can go from a CG image to a UI image pretty easily. So we'll do drawn image equals drawn. Oops, sorry. Make sure that's not nil again. And then we'll make a UI image out of our, let me scroll up a little bit. There's a constructor for just a CG image. So at this point, we know we have a CG image. It was successfully drawn. Finally, we'll make our decoded UI image by passing in our CG image here. And then just return that. And of course, if all this failed, at some point along the way, you'll just return nil. So a little bit long, a little bit verbose, but doing all this work means that instead of letting the UI image do its own JPEG decoding, you're rendering it all here on your own terms. So now, if you go back to the async image view that we were working in, we can uncomment this, or we can type it if we haven't yet, and we'll call this decoded image that we were working on. And then this will just pass back while we're in the background. Then once you have that, let's see. Yeah. Once you have that, you can just go ahead and set your layer's contents to be the contents of this. So we do decoded image. That's CG image. So a contents object is technically an id. It can be anything that is renderable. And in this case, it's a CG image that has already been rendered. So this will show the image, and it will, the layer or the view doesn't have any JPEG decoding stuff inside of it. So it'll just show this as its contents. So now that we have this, and I'll let this sit for a second, but now that we have this async image view, we can go through our app, find where we're using regular UI image views, and go ahead and use this one instead. And this class is pretty straightforward. We just take in an image, jump to the background, do our decoding, and whenever we're done, show the contents later instead of blocking main. So this is a really simplistic version of what you'd want to do in a production app, right? If you're really making a system like this, there's a lot more edge cases to think about. A lot of times you don't need to make a system like this. It's just good to know how these things work. But if you, like I said, if you use any kind of image downloading framework, it'll do this kind of stuff for you. But anyway, so let's go ahead and use this bad boy. Go ahead and copy this async image view. And you can just do a search for UI image view over in the left side. And we can just see all the places we're using image views. So it looks like our avatar, the main photo, and then in that likers view, there's 3 of them. So that's those little faces that are liking your cats. And then that's it. There's 5 of them. So if you go through and swap all those out for async image views, this should just keep working, right? Because the only difference between this and a regular view is that you set an image to it. And when you set an image to one of these, they do the rendering themselves. So let's go ahead and run it real quick, make sure our code actually works. That's always good. All right, so you do see a little flicker with the faces, right? Oh, don't break. Cool. So there is little bugs around that. But overall, we see that it's scrolling, and it's still stuttering a tiny bit, right? But it's not nearly as bad as it was. And a lot of these aren't like 1,000 milliseconds anymore, or like 500. A lot are 16, 33, 100 in like the worst case. But, or not in the worst, it was like 200 there. But overall, it's not as bad as it was before. It's almost a respectable app now. So there are still frame drops, right? So let's go ahead and run instruments and see if this did take our JPEG decoding problem off of main. And as you can see, even if the image has been there before, it's gray for a moment, right? So that is a trade-off. And a lot of these things are kind of big trade-offs, right? You're trading that moment of gray placeholder box for a lot less frame drops when you're scrolling through this feed. And that's kind of a, engineering/design decision. So, but if we stop that, we can zoom this back out. And now if you look at your CPU usage, you still have big spurts, right, with like 50%, 70%. But you have a lot of these where there's 10%, nothing going on. And then especially if you look at main. Let's zoom back out. So most significantly, your big chunks of work on main are what cause these frame drops, right? And you see like here there's 75%. So there's definitely still some work going on, but you have a lot of these like long stretches of not much going on. And if we kind of just look overall again, oh no, classic. Oh, that doesn't matter actually, so cool. Our top bottleneck looks like it's laying out sublayers. So this is another one of those things, like all this code is Apple code, but it's not the same JPEG stuff we were seeing before. And if we look over here at the times, let's see, this is 24% of the work, 600 milliseconds out of 2.5 seconds. So, yeah. And this is one of those things where if you're using auto layout, you can come in here and see layout being a big bottleneck. So the more you remove things, the more what you see here will shift around. And basically, you just have to keep doing it until you're satisfied. Like, right now, we're mostly satisfied. That was a pretty good feed. A lot better than what we started with. So let's see. That's it for that. So one thing that could happen in the code that we have so far is the one thing that you mentioned is caching. If you're scrolling back and forth, you are doing all this repetitive work. It is pretty heavy work. It's all happening in the background. But you're doing it over and over again, right? So having a cache set up to prevent yourself from doing this decoding over and over is super useful. UI image view will cache its own work internally, so you should also do that if you're going to employ this strategy. They are big, like I said, right? They take a lot of memory. So you want to use an NS cache because those will automatically clear whenever you receive a memory warning. Otherwise, you have to like respond to the event and do all the clearing yourself, and that's kind of annoying. So memory warnings are handled on main. When you get a memory warning, you get a notification on main. If you're allocating in the background, which we are, right? We're jumping to the background, allocating this big decoded rasterized image or whatever. If you're allocating in the background, those threads don't get this memo, right? So even if main dumped all its data, right? It cleared all its caches and all that. If you have a bunch of threads that are all allocating during this memory warning event, there's a high likelihood that your app can get killed, especially on older devices. Like our app would get killed in an iPhone 5, like guaranteed after scrolling a little bit. So there's a nice way you can avoid this. Instead, you can ping main first, just in case. So if you're on a background thread and you're about to allocate a bunch of memory, make sure you ping main. And that's rule number 4. Ping main when allocating memory in the background. How do we do this? What does he mean, ping? So this is how you do it. In Objective-C, you can do this perform selector on main and this wait while processing memory warnings. This can just be an empty selector, right? It's just an empty method. And what this does is you send in yes for wait until done, right? Equivalently is like dispatch main and dispatch an empty block. But you do it synchronously, so you wait until that block is done. So basically, main has a bunch of events, right? And if one of those things on the main queue happens to be, hey, clear all the memory, then this means that you'll put this task after that in the queue. So your background queue will sit here and wait until main has finished doing all its cleanup. This way, you're not blatantly disregarding Apple's notifications and getting your app killed. And then, yeah, so that's the Objective-C version. The Swift version is a little shorter, but I kind of like the explicit nature of the perform selector on main. So yeah, this is challenge number 3. I'll put the code up. We're kind of running. We want to go through this a little quickly. So we'll do this for 10 minutes, let's say. And actually, let's combine this with the next break. So the next thing is a 10-minute break. So we'll let this sit for 20 minutes. And you can take a break / try to figure this out. But yeah, in this challenge, there's 2 things you want to accomplish. You want to cache your images, and you also want to avoid these memory crashes. If you don't have an old device, you probably won't get these memory crashes, but it's just nice to know. Anyway, so now we're moving on from Time Profiler. We've gotten a good bit of experience in that, and now we're going to go to the core animation instrument. So if we do another quick trace, we will see, obviously, that we're still dropping frames. Not nearly as many as when we started, and not even nearly as many as before we were doing the JPEG stuff. But when we run, we do see that it's happening. And the trace that we see in this case, it's either like we'll see stuff like layout or pretty small stuff, or we'll see it kind of is random, but sometimes you'll see a weird trace like this where we'll drill down a little bit, and then every line will only drop down 1. And let's see, what's the next? And unfortunately, this resolution is not good, but each of these dropdowns has mock message trap underneath it. So this is like a thread weight function. So you can see that basically everything is bottoming out at these stalls. So it's not super descriptive, not super obvious why it happens. But yeah, oh yeah, we can zoom in and see. So ripc render image mock message trap, draw image mock message trap. Sometimes you'll see this. I can't prove it, but I think it has to do with what we're going to look at next. So real quick, we're going to talk about the render server. The core animation instrument is responsible for showing you stuff that happens on the render server. Let's see. So the time profiler instrument shows you the code that's running in your app, right? On the left side, we have your application. So time profiler is responsible for showing you everything that's happening in there. In general, there's this other process that's always running on your phone, and it's called the render server. And I alluded to this earlier, but this is kind of how your app works. Everything on screen happens as a result of core animation, right? So this is an out-of-process service. And so, like I said, implicitly, all your views will create a CA transaction. And at the end of the current run loop run, this transaction will be created and then committed to the render server. What this does is it creates a mirror of all your views and stuff on the render server, and then any animations you've applied or any changes to the bounds or anything will happen there, and they'll be reflected in your app. So when you do like a UI view, like .animate with duration, this doesn't affect your main thread. And if you're profiling and you notice that the actual animation doesn't affect anything, just like calling it does kind of. But the actual animation happens on the render server. That's why it used to be hard to interrupt these animations. So if you say, hey, please animate, the render server is the one that will actually do it, and then it gets reflected in your app. So sometimes you'll do things that will cause slowdowns, cause frames to be dropped, but you can't actually see in Time Profiler any reason that this should be happening. So when you get to this point, which is kind of where we're at now, that's when you want to break out. I mean, that's not when. It's when you want to break out the core animation instrument. You can do it before then if you want, but I don't like to make too many rules, man. But you can do it at this point. So it's really similar. You have a core animation timeline. The first thing, and then after that is the time profiler timeline. So this is pretty cool. And the first one is an FPS gauge. It's kind of wonky sometimes, I personally think. I think if you have your FPS printed out in the console using the math we did earlier, but with like a few extra tweaks, I think that's kind of more accurate, because if your app isn't doing anything, the FPS will drop in this view. So it's kind of annoying and misleading because you can't tell if it started dropping because you have too much work or too little work going on. So it's not my favorite. But then down here at the bottom, you have some extra options for changing, like for inspecting core animation things that might be happening. So yeah, like I said, quick reiteration. Sometimes you're doing things that are indirectly causing the render server to go slower than it should. And these options can kind of give you hints as to what you might be doing. The first one is called color blended layers. So if you turn that on, it'll color blended layers. What does that mean? For that, we have our next section, Performance Police, where I'm going to burn some apps. First is iMessage. So the nifty thing about the core animation instrument is that any of these options you turn on, you can actually leave them on and go to any app in your system and see what other developers are doing wrong. It's great. So here we see that the Apple engineers themselves are blending all these. If you turn this off, you'll see that it's white labels on top of a white background. But the red means that there is actually blending calculations happening, even though it's white being blended with white. If we want to look at what alpha blending means, you have a red and a blue box. If they're opaque, there will be no blending because one will be over the other one. But if they're a little bit see-through, say their alpha is 50.5 or whatever, when they overlap, you'll get the intermediate color. So the render server has to do this calculation, figure out what the intermediate color should be for all these pixels. So whenever you have white being blended with white, the obvious answer is white. But the render server will still do all this work, even though it doesn't really need to. So rule number 5 is avoid unnecessary alpha blending by using an opaque layer. So basically, if you set the alpha, if you set the opacity, or if you have a clear background color, all of these can mean that your view will not be opaque, and you might have unnecessary alpha blending. This is, admittedly, not a huge thing, but it is unnecessary work, and it's really easy to fix. So yeah, if a subview has the same background color as a superview, then you might as well not let this happen. So in this case, for our labels, you can make sure the opacity is 1, and you can make sure the background color is set to white. The opacity is 1 by default, so usually you don't have to do that, but you may have to fix it if someone changed it. So challenge number 4, you guys can work on this yourselves real quick, and it's pretty straightforward, but let's see. Yeah, I'll leave this here. So fire up the core animation instrument. Once it's going, turn on color blended layers, and then go through the app and see if you have any blended layers. I'll leave this here for a couple minutes, and then I'll start doing it myself. But I just want to give you guys a head start. All right, so like before, do Command-I, start instruments. And, oh shoot. We can stop that and kill it. So if you're in a view like this where instruments is on, you can just do Command-N, and that'll let you pick any of these templates and restart. And you can do that at any time if you want to start using something else. So core animation. And so here we can't, I mean, this is a useful quick look, right? You see 52 frames per second, 56. So you can see that you're definitely not hitting 60. I've found also that even if you have a table view with literally nothing in it, this will say like 58 across the board. So it's, like I said, it's not the most reliable, but it gives you a rough view of what your FPS is. All right, so down here in the debug options, we can turn some of these on. So let's start with blended layers. And if we look at our app, we see that we too have fallen prey to the classic mistake. So all of these are red, but they are white labels on a white background. So we can go ahead and fix that. Pretty easy. So, and there should be, if you come to the cell, so these labels are all in the cell. So search cell.swift, go to the cat photo table view cell. So it's all these labels. I didn't look at which ones it was, but let's see if we come down. Cool. So yeah, there is a comment in there for set background layers or background colors for labels to white. So by default, the background is clear, and that is useful if you're, if you want things to be see-through with your text. But in this case, it's white. So let's see. There's the username label, so we'll change that one. There's the photo time. There's the likes. And what's the last? Oh, the description. So as you can see, this is not super hard to fix, right? But it is something to be aware of. So that should be it. Let's go ahead and try again. And so now we see that our labels are all fixed. Oops. These images look like they have some blending, but that's not a huge deal. That goes away once the images load. But the weird thing is our shadows are all jacked up. So labels are kind of weird about shadows. If they are a clear background, then the shadow will mimic the shape of the letters. If they don't have a clear background, then they will mimic the outside of the box. So we kind of broke our shadows, but we did fix the alpha blending. And we can go ahead and fix the shadows later. So we won't worry about that for now. But we solved our alpha blending problem. All right. So that is, like I said, the alpha blending thing is not necessary, so you don't want to do it, but it's not the biggest deal in the world. Next, the more important one by far is something called color off-screen rendered yellow. And here's an example of it in the Instagram app. You have these circular, profile pictures up top here, right? When we turn this option on, we see all this yellow up here. And the annoying thing is when we do this recording, I think it records at 30 FPS, so you can't really see. But the interesting thing about off-screen rendered is that it happens on every frame of your drawing. So it ends up resulting in very consistently worse frame rates. Versus a time profiler like bottleneck. A lot of times that'll be like a sharp, stop in your scrolling, and then it'll continue. But with this, it's just kind of all around sludgy. I think if you pull out Instagram, even on like a 6S, and play with these bubbles long enough, you can start to notice how sludgy they feel. So nobody's safe, nobody's perfect. And then if you use the Twitter app, go to the profiles. This is not slowed down. This is a real-time capture on my 5 of this profile expanding. And as you can see, there's all the blending, of course, and that whole section that expanded was off-screen rendered as it was animating. And once you get past the profile, it starts scrolling normally, but at the top, it's almost unusable. So yeah, off-screen rendering can be a much bigger deal, and you can't see it in Time Profiler. So one thing that we need to talk about real quick, let's see. So what causes off-screen rendering? It happens when a layer doesn't fully know how to draw something that you've told it to. So there's a few cases where this happens pretty consistently. We saw on Instagram the corner radius property. So if you have round images or round views, you don't want to use this corner radius property. There's better ways you can do it. It's not, like I said, it's one of those things where if you don't care, maybe it's not that big a deal, but it will consistently make your scrolling slow down. Should rasterize is kind of a weird, it's a property that can be useful, but you have to know all the ins and outs of it, and if you don't do it right, then it is guaranteed to introduce off-screen rendering on every frame of your drawing. So it's pretty dangerous. I don't think it's worth using, honestly. I think there's plenty of better ways to get around excessive drawing. Rendering shadows. If you have shadows that are being drawn, if you do them incorrectly, then this will guarantee you have off-screen rendering. I'll show you what incorrectly means in a moment. And then the UI effects views. If you use the blurs or anything like that, if you see Apple people talking about it, they say, make sure there's no animation under it, make sure you blur as little as possible, make sure you cache it. There's a lot of, easy ways to kill your app if you use a lot of these blurs. So one thing that is, I think, kind of interesting is I mentioned off-screen rendering earlier in the talk. And this happens in dub videos a lot, I feel like. The engineers will use this phrase, off-screen rendering, for two completely different things. So the first version of off-screen rendering is what we talked about earlier, when you do drawing on the CPU. So when we did that decode JPEG stuff, that was drawing and it happened on the CPU. So that was technically off-screen in that it didn't go to the GPU to be drawn. That type of off-screen rendering is kind of a pros and cons thing, right? Maybe you can make it faster on the CPU. Maybe there's reasons you want to do it there. Like in our case, we had the pro of being able to do it concurrently. So that's a good or bad thing. But you want to do that on purpose, basically. This type of off-screen rendering actually means that you've done something that you have submitted a CA transaction to the render server. And then on the render server, out of your control, it tries to draw something like a rounded corner or a shadow, and it doesn't have all the information it needs to do it. So it stalls, jumps back to CPU land, and does the calculations it needs to get like the shape or whatever it couldn't figure out. And then it jumps back to its GPU rendering stuff. And when it does this stall, it like clears all its caches, and there's a bunch of stuff that means this stall is actually like a big deal. So the real killer in this off-screen rendering is the GPU stalling on every frame. And this kind of off-screen rendering is never good. It's always bad, and that's why it's confusing that they use the term for both things, because this is never cool. So rule number 6 is don't use the corner radius property, and really all of those that I mentioned should be used carefully. So just don't do it. It's not worth it. Instead, you can use a Bezier path. This will make it the same as earlier. This is the good kind of off-screen rendering compared to the bad. So in this case, we have another image method to add to our UI image extension. This one will take in an image, and it'll just return an image that's been rounded. It'll base it on its own size, so you don't have to worry about like, if you want to do custom corner radiuses, then you can pass that in. But here we're just making a perfectly circular image. So once again, this is a little bit different. The other one we used core graphics. You could do this with core graphics, but it's a lot longer. So this is the UI view version of those core graphics drawing APIs. You can pick whichever one you want, but they're basically the same thing. So demo number 5, let's go ahead and do some corner rounding. OK, so we have a few round images. I don't know if you noticed them when you were playing with the app, but they are the liker images. So this time, we're going to do basically the same thing as we did for our async images. So let's go to our views, and we have our async image view. And we're going to make another custom view, and this one will have perfectly round images whenever you add an image to it. So basically the same idea. So the class will be rounded image view. It'll be a UI view again, and it'll be Swift. So add that to your view folder. Kill those comments. OK. So like before this, like I said, you can honestly like copy and paste the other code if you want. But I'll type it out just to drive it home. And once again, so this, like I said, this drawing, this is the first kind of off-screen rendering. This drawing is slower than doing the normal just image view.image equals image. So we'll want to jump to a background queue for this also. And that way we don't lose the benefits that we had earlier by doing background rendering of the views before. That out. OK. So I'll wait for a couple minutes. But basically the same stuff. Literally the only difference is that we are going to call this circular image function that we're about to write. A good programmer would, not duplicate code like this, but it's fine for now. All right, so let's jump over to the UI image extension. And then below our previous method, we have a circular image method. So this is another class function or method. go from an image that gets passed in. And then we pass in the size. So here we're going to pass in, this will be the size of the view itself. So we want to do the rounding to shrink the image down and make it a round image the size of our view. If you round a giant image, which they all are, then it would look weird in your view. So that's important to remember. And they would render really big, and if you do that, your app would run out of memory like instantly. So, oops. So we got to get the scale. Let's see. So this rendering needs the scale of the screen. So we'll grab the scale real quick. And then we make the rect that we're going to render into. So we take the size that's passed in, and we multiply the width by the scale, and then for the height we'll do the same thing. If you say you don't do this and you just use the size, height, and width, you'll get low-res images that look, grainy and ugly. So, and then this is a little bit different. So instead of making a context and using that object, this is kind of the alternative API. I think they're both wonky, honestly. But so this one, fix begin image context. So we're beginning a context, we're passing in the size, and we want to make sure to use the one that has the expanded, the correct size where it's multiplied by the scale. They don't have to be opaque, so we'll pass in false for this. Or they need to be opaque, sorry. And finally, let's see. Yeah, we'll just use the height. Just do this. Cool. Oops. Oh, my bad. This is just the scale. Ignore that. Okay, so you pass in the size, and then you pass in false because we want it to be opaque, and then you pass in the scale. So this will know how to draw it correctly. And so in this case, the actual context is kind of like, it just is in memory now. So you start the context, you do some things to that context, and then you close it later and with the drawing. So in this case, we'll make a Bezier path. Bezier paths, if you ever want to draw a circle, Bezier path's the way to go. So let's see. We'll make a circle path. We'll use this constructor, the rounded rect with corner radius. So that's pretty straightforward. We use the rect. And then for the radius, we can just divide, let's see. We can do, the width. Technically, it doesn't matter, but in this case, we'll take the width. We're assuming it's the same size, height by width, and dividing by 2. So this will make a perfectly circular image, unless you pass in a weird size. And then what you have to do next is you have to take the circle path, and you have to call add clip. So the reason I think this all is kind of wonky is like this add clip affects the image context that you started a couple lines ago. And that's not immediately obvious just by calling this method on this object. But so adding the clip means we're adding this path to, and we're clipping it based on the circle. So now that we've clipped it, we can just draw. So just take the image and we call draw. Oops. And we'll call draw in and pass in the circle rect. Oops. And so like I said about starting and ending the context, to get the actual image in this case, you have to call UI graphics get image from current image context. And this will do the actual creating of an image from what we just drew. If that's successful, then we return the round image. And like before, if it's not successful, we return nil. All right. Now that we've finished that, let's go back to our round image view. And go ahead and finish this. So UI, we'll get a round image. We'll call UI image.circular. Pass in the image we just got. And the size will be self.size. Bounds.size. Then self.layer.contents. There. So we make a circular image, make sure it's the size of this view, and then just set the layer contents like we did before. Now that we have our rounded image views, we'll go to the likers view. So this is the only place we have circular images happening. And we did change this to be async, right? But now that we have this round one, we can do this and just use those instead. And now that we're doing this asynchronously under the hood without affecting the GPU, we can come down here. Let's find, right here, it looks like we're setting the corner radius to 12 for each of these views. Instead, you can just remove that. So you don't need that anymore. You do need to make sure that your liker view clips to bounds equals true. So if a view doesn't clips to bounds, then anything underneath can stick out. And in this case, I think this is necessary. So let's go ahead and try it out. And it's funny how this will just get stuck like this a lot of the times and just kind of hang around for a while. So if you look at the liker views, you'll see that they're all red, right? So they do have alpha blending, which is kind of a necessary trade-off in this case. There is a way to draw circular images without having alpha blending, but it's a little more work. You can look into it later, but yeah, in this case, I chose the easy code over the completely perfect. If you want to make it completely perfect, you totally can, but this is pretty good for now. But yeah, as you can see, don't have that off-screen rendering anymore. So that's pretty nice. And actually, oh, you know what? Let's just make sure of that real quick. That's not quite right. So let's turn the blended layers off because that's annoying. And then make sure off-screen rendered yellow is on. Okay, so this is what we want to look at. So as you can see, there's a ton of off-screen rendering. That's not good. But if you look at our likers view, it is not currently off-screen rendering. So neat. We still have the profile view, so let's go ahead and fix that real quick. Go find the user avatar, change this to a rounded image view. And then if you search for that, you should be able to find a layer.corner radius. So now we can go ahead and get rid of this corner radius usage again. And that's down at it was at like line 83 in the cell. So try again. No. Yeah, that must have been a cached version or something. But, oh no, that's not true. Okay. So we still didn't fix it. We did fix the corner rounding, but it does seem that it's still showing up as off-screen rendered. So it looks like there's still weird stuff going on. So let's go back to the slides and see what else we can fix. All right, so we fixed the corner rounding, but we still see a ton of off-screen rendering. So what else is there? So shadows. We have shadows on the text. We want to draw shadows the right way. I'll do that in a second. So this is an example of when shadows are bad. This is, if you ever see someone using the label.layer.shadow, color, offset, radius, opacity, if they're only using these 4 properties, that's real bad. But if you add, there's 2 ways to fix it, basically. If you're trying to fix text, then you can use an NS shadow and an attributed string. If you're trying to fix just a regular like square UI view, then all you have to do is add a 5th property called shadow path. In this case, you create a Bezier path. You say, I want the Bezier. It's the same as the path we created earlier. You give it a CGRect, say, be this shape, and this will no longer do off-screen rendering. So this is a very obvious case where like you're literally not giving it all the information it needs. You're giving it enough to figure it out, but you want to make sure to use that 5th property, Bezier, or the shadow path. So this is a quick example of what I explained earlier. You want some shadow in here, goes to the GPU, it doesn't have enough info, goes back, gets the information it needs, puts together. And so all these stalls between the CPU and GPU are what cause all the slowdowns. Frame buffer, that's a fun fact. Frame buffer means the screen, if you ever hear that phrase. All right, so I'll draw shadows the right way. I'm going to combine this with the next demo. My personal opinion, just for the love of God, don't use the should rasterize property, especially with big images. The rule is if you are trying to cache things that you think will be reused a lot, you only have this should rasterize does some like automatic caching for you. But if the cache it only is the size of 2.5 times your screen size. And if you put enough stuff in there that it kills the cache, then you'll just aggressively start dropping frames all the time. And it'll just off-screen render like crazy. So not really worth it. Here you're doing too much. Should rasterize equals true. You don't do that. It's bad. Some people would argue and say it's totes worth it sometimes, but I don't think so. So here's a summary. Let's go ahead and do those real quick just to see them. So the easy one, let's go ahead and fix the should rasterize. Literally just come over here, search for should rasterize. Oops. See a couple instances, and you get rid of those. And they're all right together. So basically there's 4 right in a row. Just go ahead and kill those. Oh, 6 even. Wow. Cool. Make sure that's not in there. We'll check that out. All right, so that's looking better. Now these big images aren't doing it anymore. And the problem we thought we fixed earlier with the avatar is now fixed. That's not off-screen rendering. So the only thing left is these 3 labels. And this is because we're doing the bad kind of shadow. So let's see if we can't fix that shadow real quick. So in this case, we have text shadows, right? And we don't want it to be the shape of the box. We want it to be the shape of the text itself. So this is the case where you would use the NS shadow property, or NS shadow object. So let's go find that. Shadow. So if you're in the cell, you can search for this apply shadow function. Let's see. That wasn't useful. There we go. So if you, let's see, search for that. We're just calling this method applying a shadow to each of these labels, right? So the method we're using is that bad method that I've mentioned. You could come in here and say label .layer.shadow path, and then give it a CG path that represents the square, right? But like I said, we don't care about the square. We want to make text-shaped shadows. So let's comment these out for now. And so instead, let's see. First, we want to guard. We want to make sure that basically we're going to take these images, or take these strings, take all these labels, grab their strings off, recreate the attributed string, and make it with a shadow. So let's make sure that there's some text there. So the first thing we'll do is we'll make an NS shadow. An NS shadow is basically an object that wraps up all these shadow properties into a single object, and you pass it on to UIKit. So equals NS shadow. So one funny thing is there's no shadow opacity with an NS shadow, so you just have to add that into the color. So when you make the black color, you'll make it with an alpha of 0.5. Kind of a weird little difference. So you make the shadow color, you make the offset, make it the same as the offset was before. So you can pretty much just copy and paste each of these things. Shadow.radius. Copy and paste that 5. All right. So yeah, these 3 properties represent these 4 properties that we were applying a different way before. Now, we'll just create an attributed string, which hopefully you've done before. It's not too crazy. You got to make an attributes dictionary. And so there's NS attributed string keys, and there's just a shadow key. So you can use that and give it the shadow. You also want to set up the font. So just make sure it looks basically like it did before. Label.font. So now we'll make the actual string with the string and attributes. Cool. So here we'll use the text that we got with the guard earlier, and then we'll just use our attributes object. Cool. Sorry. There we go. Okay. So basically we grab the text, we make a new shadow with a separate shadow object, and then we just make an attributed string. So let's go ahead and try that. Oh, dang it. And now you can see that our text does have a light shadow underneath it. It is in the shape of the text instead of a square around it. And the only off-screen rendering left is our status bar, which for some reason has always been true and seems like it always will be. So Apple, I don't know, they just do that. So anyway, yeah, that's Our app is now successfully clean as far as core animation goes. There's no, shouldn't be much red. Let's see, color, blended layers. Yeah, so these images, like I said, you do trade off-screen rendering for alpha blending, but alpha blending is like leagues better than off-screen rendering. And just scrolling around, like this looks a lot better than it did before, right? So, and yeah, there is that other method for getting rid of alpha blending. But anyway, that is it for that. Okay, so quick summary of the core animation section. You want to avoid blending and off-screen rendering. There's a bunch of other controls in there, and you can look up what they do, like misaligned images and stuff like that. And each of them is pretty straightforward to fix, which is nice about the core animation instrument. It can give you a lot of like easy wins. So blending, make them opaque, off-screen rendering. Don't use the things we talked about: shadows, corner radius, should rasterize. I'm sorry. Fool. Yep. So that's it for the session. Conclusions: where to go from here, where we've been. Overall, you should be tracking performance in your app. This is something that I don't think a lot of people do. A lot of apps you'll download. Once you start looking at this stuff, it kind of opens your eyes, right? Like this, like there's like glass shattered moments the more you look at like how many apps drop frames a lot. So you can use a display link in your app. You can add performance tests, which we didn't really get into, but those are pretty nifty because you can performance test a particular piece of code, see if it's regressed, see if it's gotten better magically. Use Time Profiler to get an overview of what's happening in your app on the CPU as a direct or indirect result of code you've written. And then use Core Animation to see when you're doing things that are indirectly causing the GPU to stall or do extra work. We went through a bunch of rules. So let's see, use display link, don't do I/O in the main thread, decode JPEGs in the background, ping main during big allocations, avoid unnecessary blending, don't use corner radius, use shadow path, and don't use should rasterize. So if you follow these are kind of real big picture things I've noticed as I've been doing performance stuff on our app. There is a lot of, I'm sure there's plenty of more rules you can make up, but these are nice ones to know. So where to go from here? If you thought instruments was fun, you think performance stuff is cool, there's a lot of places you can learn more about them. I didn't get into memory, really. That's kind of a separate issue in my mind, but there are a couple instruments that are super useful for debugging memory, leaks, cycles, stuff like that. So that's pretty useful. Energy, there's an energy instrument which will tell you if you're doing work that isn't necessarily slowing down your app, but it is draining the battery unnecessarily. So that's a pretty nice instrument for that. Stuff like networking, excessive networking, and stuff like that. So if you want to learn more about this, I do have a video course on instruments where I go into more detail on the memory ones, optimizing launch times. I think I end with one on the energy gauges and stuff like that. So that's not bad. And then if you want more performance specifically, there's a really good book that I read and I recommend, and it's by Marcel Weir, and it's called iOS and macOS Performance Tuning. You can get it on Amazon, on Kindle. So this book goes into some really like in-depth, just big picture performance things. It kind of crosses, it focuses mostly on Objective-C, which is interesting. He has a whole chapter on why if you're doing something really performance intensive, you should just not use Swift, which is very offensive to some people. But it's pretty interesting chapter, I think. And yeah, so it's got a lot of kind of low-level performance tips and stuff like that. And he worked at Apple for a long time. He works at Microsoft now, I think. So it's pretty trustworthy, I think. Yeah, mostly Objective-C. So go forth, make Steve happy, make your apps performant, make your users happy. And if you want to get in contact with me, I'm at Luke Parham on Twitter. I have a website and an email. So feel free to follow me on Twitter or email me. Yeah, that's it.